when you could, in fact, do something with it. But I was also asked whether the reverse is true. So in certain contexts, I think, so later on when we talk about linear operators, roughly speaking, there's something like that, but I just want to clarify that we don't use this directly, as far as I can tell. So don't worry about this, the reverse. Don't worry about the reverse operation. We will use something, we will take the adjoint of the linear operator. So we'll talk about that part. But that's where we use the adjoint, both for converting text into bars and also for taking the adjoint of linear operators themselves. But otherwise, we don't usually, as far as I can tell, as far as I can think of it, we don't usually convert bras, standalone bras back to cats. Yeah. Okay, so I wanted to continue with our discussion. We were basically done with the basics of what an inner product is. So we know what a vector space is. Now we know what the inner product is. And for the homework, you're going to try out for yourself to verify a bunch of different inner products. There's one that was involving an integral, one involving the trace of matrices, and the other one is just a complex, the complex generalization of the usual dot product. So let me just start with a result that you can in your homework, namely the Cauchy-Schwarz inequality. And the reason why almost all the quantum mechanics books will mention this is because this is in fact going to show up later on when we talk about the uncertainty principle. Okay. So what is the Cauchy-Schwarz inequality? It says that the inner product of alpha with itself and times beta with itself obeys an inequality that is greater or equals to the square of alpha beta. So at this level, maybe it looks a bit abstract, but the analog should be familiar from basically geometry, which is if you take the dot product of two vectors, right, then basically you can show that the length of x squared and the length of y squared is greater or equals to x dot y squared. Okay? And of course you can ask why, because this guy, x dot y, remember, for geometry is given by x squared, y squared, and a cosine theta squared, right, where cosine theta refers to the cosine of the angle between the two vectors. Right? And so cosine runs between -1 and 1. So when you square it, cosine squared will run between 0 and 1. And therefore, there is a bound on that dot product. The dot product cannot be greater than just the square of the product of the lengths because of this cosine. Okay? So it's an analogy. It's not a proof because what's the geometry. But now you'll see that there's an alternate way alternate way of looking at this using this more abstract notion of inner product. You try to figure it out for yourself. There is a clue in the homework problem. And so hopefully you can figure it out. Just think about it for yourself first. Okay. So we have talked about it in the product, so therefore now we can have a more abstract version of orthogonality. Right? So when it comes to the inner product or dot product, you say that two vectors are orthogonal when their dot product is 0. Right? And so of course in this case, for vectors, this is because for the same reason, is u times w times the cosine of the angle between them. So you want to say that it's orthogonal because when theta is pi over 2, the cosine goes to 0 and the dot product is 0. So likewise, but it's an analogy, we say that alpha and beta are orthogonal when the inner product is 0. So remember, this is in general a complex number. Right? It's no longer just the usual dot product. So alpha beta are usually complex. But it is 0, that means that it must be equals to its own complex conjugate. Because 0 star is 0. Right? So I can write it as either alpha beta equals to 0 or beta alpha is 0. And remember that the only thing that has, I should mention, there is something called the norm. It's just definition. So is this, right? So we define orthogonality to be when the inner product is 0. Now I should say the norm of a vector is basically the positive square root of the inner product with itself. So this is the norm of alpha. Okay. So what I want to say is what I want to say is that because it's the only thing that has 0 norm, 0 length essentially. Right? So this is the analog of length. But it's not exactly the same thing. Mathematicians usually like to say, give it a different name. Right? They like to be very precise, which is of course highly respectable. Right? To be very precise is highly respectable. But sometimes too much jargon is very confusing. So think of it as just a length. Right? It is just a length. Now what I want to say is that the only thing that has 0 length and 0 norm, as we say, in linear algebra is the 0 vector. So basically anything can be made, can be normalized to have unit norm. So if you start, so I'm going to say any alpha that is not the 0 vector can be normalized to 1. So why is that the case? So we just have to consider alpha hat. And you take the original vector and you just divide it by its norm. Right? So you may recall, if you have a vector and you want to make out of it a unit vector, so usually we put a hat on top of it. So what is that? So likewise, you just take V, and then you take the original vector, and you divide it by the square root of the dot product. Okay, and it's the same reason why they are now of unit length, right? It's the same vector in, I mean, it's not the same. It's the same direction, but now you have normalized it to unit length. But it's the same reason why, because now you can just calculate directly, right? Alpha hat. So remember that the norm you will find is a real number. I should say this is always real. In fact, it's a very simple homework problem. You can prove it for yourself. It's always real, right? Because you might ask this question because I already reminded you, alpha beta is usually complex. So how do you know alpha is real? You should think about that. But if you believe that it is real, then when you take the adjoint, remember this is alpha adjoint alpha. Oops. Yeah, alpha hat, adjoint alpha hat. So what is that? This is the adjoint of, or the dagger of the square root of alpha. This is just a number. So remember the rule is that when you take the dagger of some complex number times a cat, you get a complex number star times the corresponding bra. So this becomes a bra, and this number is just a complex, becomes a complex conjugate. But this is real, so you can just multiply it, and you realize you get alpha. And then in the top, you also get alpha, and therefore it's just 1. So again, if you're just confused by the symbols, confused by the abstract character of the calculation, just remind yourself of the dot product, which hopefully is more intuitive. All this discussion is leading up to an important fact. Okay? So these are largely definitions. Orthogonality is the definition. Norm is also a definition. This is an observation. You can always normalize your vectors to unit length. But all these tells you something that it's going to lead up to something, which is the following statement. So let me just write it as a fact. Given a basis so I put I prime to indicate I will run from 1 to D, the dimension of the vector space. Okay, and but remember that a basis can be anything. Right? As long as they're linearly independent, they form a good basis. As long as they maximize, is the maximum number of linearly independent vectors, that gives you a basis. But it need not be unit length, nor do they need to be mutually orthogonal, right? But the fact is that they can always be made to be orthogonal. And unit length. I.e., orthogonal. orthonormal. Orthonormal. Okay. So I think I'm gonna skip this because you know it's a discussion that I'd like you to read for yourself. Partly because I suspect some people don't read my notes because it's all in English, right? One of the things I learned in Taiwan is that if you write your notes in English, nobody reads it. So I'm going to just skip this and ask you guys to read it. But I will say just a few words about it. Okay? So the main point, the gist of the argument comes from the following observation. Okay? So if you already have a bunch of vectors that are orthonormal, so let's say you have 1, 2, all the way to n. That's why I put a prime here. The unprime vectors, usually I would denote them as orthonormal. Usually, not always. Oh, by the way, I should say, so now I put the basis without the prime. So let me just write down in something first. So in symbols, in terms of notation, that means that I should be able to find a basis such that this will give me Kronecker ij. Okay, so this is just a mathematical equation that encapsulates what I'm saying here in words, right? If it's orthonormal, it means that when I equals to j, you're calculating the norm or the square of the norm, but it must be 1. Okay, because the norm itself is 1, so the square is 1. But if they're orthogonal, then when I is not equal to j, when you're not talking about the same vector, then the inner product is 0. Right? So this is just a succinct way to write down an equation, is what I'm saying in words. Okay, so back to what I'm saying just now. So the observation, the key observation, behind what is called the Gram-Schmidt procedure. Is that it gives you an algorithm. It's not the only one. I don't think actually there are kind of refinements to this. But I just want to give you a algorithm so that you can see how that it can be done. Given a vector basis, there's a procedure, namely Gram-Schmidt. You turn the crank, and then out will come an orthonormal basis. And the underlying fact is kind of like that. So maybe I'll draw a picture first. First for vector calculus, right? So if you have a vector v, and you have another vector that's already unit length, let's say e hat. Okay, so let's say e hat, and I just want to extract the component of v orthogonal to this. So we know pictorially this is v perpendicular, right? Meaning is the component of v perpendicular to e. Well, how do you extract that component? You see, you take v, and then you want to subtract off basically the component parallel to E. Right? So E, remember, is unit length. And so what you do is you basically subtract off the component parallel to E. But what is the magnitude? The magnitude, which is this length, is of course just a projection of V along E. I hope at least geometrically this is clear. So the linear algebra version of it is actually a simple generalization of this. So of course, if you have multiple E's, so if you have many E's, then you just project them. If you have a bunch of E's, so what I mean by that is that you have a bunch of orthogonal directions, E1, E2, E3, and so on. Then V perpendicular will just be V, and then you subtract off the components of V parallel to all these vectors. Okay. And so the generalization of this for linear algebra is that if you want to construct the vector that's perpendicular to a bunch of orthonormal vectors, then what you do is you take the original vector and then you, just like this guy, you subtract off all the components parallel to these n vectors. That's the key point. Once you realize this, then you know that the rest are details in the sense that you have to, at every step of the way, you have to normalize the vector to 1 and so on. But otherwise, this is the key step. Where once you understand, all you're doing is just projecting out the components parallel to the other vectors, then you understand the process easily. So, like I said, I'll let you read up on Grand Schmidt yourself. There's even an example. So it's just 2 pages. Like I said, I strongly suspect that many Taiwanese students, once it's in English, you don't read it. Please do. And then for your homework, you would actually construct the Legendre polynomials. Right? So I kind of gave it away already. But I was even asked this question the last time. Why do we care about inner products like this? Okay. If you guys remember, this is actually the example of one of the examples of the inner product. And the examples I give, you will discover all of them will show up in physics. That's why I give them. So the reason why this one shows up in particular is that when you often do a integration over the sphere, so if you integrate over the sphere, any function, let's see, yeah. So we will simply do integrals like this. If you do an integral over the sphere like this, involving 2 functions, you'll find that the cosine part of this, so d omega, what is d omega? It's d d cosine theta d phi. Okay, that's a solid angle. So if you use the variable cosine, if you let cosine be x in this case, then in fact you'll find that cosine will run between -1 to 1. And at least for the cosine part of the integral, you are just doing dx from -1 to 1. Of course, the phi will still go from 0 to 2 pi, but the cosine part will go from -1 to 1. So the Legendre polynomials you will discover are basically is a special case of what is called the angular spherical harmonics, which again we'll talk more about. One of the things I want to emphasize in this quantum mechanics course is the role of symmetries. Right. Actually, this is also the perspective taken by Weinberg, so you will see that the angular spherical harmonics are a big part of the discussion of rotational symmetry, and we'll see in due time why it is so. But you'll find that the set of polynomials that are orthogonal, not orthonormal, because they're not on unit length, but orthogonal under this inner product is in fact the Legendre polynomial. So in fact you will discover PL or Pn of cosine theta will turn out to belong to the spherical harmonic, the class of angular spherical harmonics. So angular spherical harmonics. And that is why it's important. Any questions for me? All right. All right. So, the next observation I want to make is about the relationship between orthogonality and linear independence. So I think it's fairly intuitive if you're doing vector calculus that if a set of vectors are orthogonal, then they are immediately linearly independent, right? So it's like telling you that, okay, let me give you the x-axis, the y-axis, and the z-axis. And because they're orthogonal, you can immediately tell, it's intuitive, like I said, that they are linearly independent. But the key, as we will see shortly, is that you can, of course, make it more rigorous. And the key behind that is their orthogonality. Right? So, and this is a very useful observation because that means that if you have, for example, a set of orthogonal basis, if you have a set of orthogonal vectors that are also equal to the dimension of your vector space, then you know immediately you have a basis. Okay, so let me just see this. So let's say they are not. So it's kind of proof by contradiction, right? So suppose they are not. Suppose these guys were actually linearly dependent. So what does that mean? It means that you can superpose them. Remember that Ci upstairs doesn't mean it's power. It's just, I just like to write my indices upstairs. Right? So it's just a bunch of numbers that you use to superpose to get your, to superpose your n vectors. And if you suppose that they were linearly dependent, it means that there must be some non-trivial coefficient such that you can get 0 upon superposition. This is what it means to be linearly dependent. But now they're orthogonal, right? So I can now project or act J bra on both sides. Of course, again, remember 0 here just means the 0 vector. I'll be very sloppy because I think I can. When I write 0, I just mean the 0 vector. Okay? So if you do act it on both sides, what happens is that you get Ji and then you get sum. Right, and of course it's a 0 vector, so anything acting on it is 0. It's still 0. Okay? Now, I don't need to assume that orthonormal, but as long as it's orthogonal, what does that mean? It means that as a sum over I, as long as the I is not equal to J, is 0. Right, that's what orthogonality means. As a sum over I, as long as the I is not equal to J, those terms are 0. So the only thing that is non-zero is the term where I equals to J. So you get Cj, J equals to 0. Well, what does that mean? Remember, these are non-trivial vectors. So this is not 0. This is not 0. Otherwise, it would be the 0 vector, and there's nothing to talk about. So therefore, actually, Cj must be 0. I've not assumed anything about J. Right? J can be any one of these guys from 1 to n. What does that mean? It means that all the C's must be 0. C1 is 0, C2 is 0, all the way up to Cn is 0. And that immediately contradicts. So, contradiction. That immediately contradicts our original starting point, right? Which is that they are linearly dependent, and therefore it's false, right? Once you run into a contradiction, it means that your original starting point is bogus, is wrong, right? And therefore they are all linearly independent. So let me repeat what I said earlier in words, which is that once you know that this is true, so if you have a set of if you have a set of G orthogonal vectors, so right now they don't need to be orthonormal, but we already talked about this, that if they're not unit length, you can easily make them unit length, right? But so once you have The key point is once you have found a set of D vectors that are mutually orthogonal in a D-dimensional space, then you're done. Then you have in the sense that you have a basis. Right? You don't have to do any more work. Maybe you have to just normalize them, but otherwise you don't have to work hard to find a basis, an orthogonal basis anymore. Right? So, and I hope it's clear because D is a D vectors and they're orthogonal. Then by this discussion, you know they're all linearly independent. But if it's a D-dimensional space, that means that you will have at most D. You must have D. Maximum number of linearly independent vectors is D, and you already have them. So therefore, the basis. So you found the basis. Okay. So let's just give you a simple example. So we're doing quantum mechanics. So I assume that you all have seen the Pauli matrices. So when you're undergrad, you learn a spin, presumably, by saying that spin is basically the Pauli matrices over 2. Right? Maybe there's an H bar, but I'll talk about H bars in a little bit. I assume you guys have all seen this. Right? So sigma over 2 is the spin operator. So for example, a very common interaction between spin and the magnetic field is just spin dotted into the B field. Right? So this is part of your, usually this is part of your Hamiltonian. The interaction between electromagnetic fields and the spin of the electron. This is a very important part of how we discovered spin in the first place. Now, what I want to say here is that the set of Pauli matrices, so I can be 1, 2, or 3, together with usually what we'll call the zero component, which is actually just the identity. This is just notation. But with this notation, I can call this sigma mu. So mu will run from 0, 1, 2, 2. Okay? So it turns out that if you try to compute the trace of, let me put a hat on it to denote that is a matrix. If you try to compute this guy, right, so remember that for matrices, you can compute the inner product as a trace. So I'm going to take the mu kind of inner product with the nu, then I will need to take the dagger, the matrix adjoint of mu multiplied by nu, and if you do a calculation, you will find the following. You will find that, I just want to make sure I get my normalization right. You will find that this is actually 2 Kronecker mu nu. Okay? So up to this factor of 2, you discover that these guys are orthogonal. That means mu, these matrices are mutually orthogonal. Okay. But let's think about it. What are they? These matrices are 2 by 2. Right, so these guys are 2 by 2 complex matrices. Actually, only one of them, depends on the basis, but anyway, they are complex bases. So, well, if you have a 2 by 2 complex matrix, what's the dimension of this guy?
4.
4, right? So let's write down the basis for it. So tell me, what's the first basis? 1, 0, 0, 0. The other one is 0, 1, 0, 0. And then you have another 0, 0, 1, 0. And then you also have 0, 0, 0, 1. I think I had a question the other day about how do you tell what the dimension is and so on, right? So in physical applications, usually you can tell right away. And so this is a basis, for example, for the set of all 2 by 2 complex matrices. But now you have another one. Okay, I don't even need to tell you what they are explicitly, just by virtue of the fact that these Pauli matrices, together with the identity matrix, there are 4 of them, right? So there are 4 of them, and because they are mutually orthogonal, right away from just the discussion that we had over there and over here, you can tell right away that these are a good orthogonal basis for your 2 by 2 matrices. So in fact, in many applications, even in neutrino physics, you will discover that often people use this basis to do concrete calculations. Right? So I just want to give you an example. You see very often the Pauli matrices used as a basis, and now you know why, because they are orthogonal. Any questions for me? No?
So,
yeah.
What is the advantage of using Pauli matrices in your calculations in this far more complex than the simple matrices?
Yeah, because they're orthogonal, right? They're orthogonal. That's the key point. They're orthogonal. Yeah, we can calculate. These are orthogonal. Let's calculate. 1, 0, 0, 0 multiplied by, let's say, 0, 1, 0, 0. You get 0, 0, 1, 0. Okay, so this is orthogonal to that. So it might well be orthogonal as well. I have to calculate the rest, right? But you have 4 choose 2. So it's a good question, of course. But like I said, one property is that they are orthogonal. But you don't know whether these guys are orthogonal, for example. But I need to calculate through this basis. But if someone can do the matrix multiplication quickly in their head, you can tell me. So they might well be orthogonal as well. But again, we do know that Pauli matrices are perpendicular. So they make a good, intuitive basis for your 4-dimensional space. The other reason for it is because of the special properties of the Pauli matrices. For example, I just mentioned that sigma is a good basis for describing spin of the electron. So that's another reason. At least the sigma I part. Right, sigma 0 is just the identity. But sigma I part is a good basis for talking, is a good set of matrices to talk about spin. And then later on, when you do even relativistic quantum mechanics, when you do relativistic quantum field theory, in fact, they will show up again. They will show up also as a related to the Lorentz group. Right? So we're doing quantum mechanics here, so we won't see that part of it. But the reason why I always take the chance to talk about Pauli matrices is because it shows up everywhere in fundamental physics. Every time we talk about spin, when we talk about quantum field theory, or at least relativistic quantum field theory, you will most definitely encounter them. Like they're intimately related to what the concept of these objects called spinors. Yeah. Good. Any other questions?
So
Yeah.
is that analog of Pauli matrices?
Which one?
Not those.
This?
Yeah.
No. They're not permission. Yeah, they're not permission. These guys are all permissions, right? So for example, you take the trait, if you take the Geiger of this guy, you get this, right? So they're not. These guys are permission, but not these guys. Yeah. Yeah, don't be confused. I don't mean that these are the Pauli matrices. I'm just telling you that you can easily enumerate what the dimension of this space is. Right. That I don't mean to say that those are the Pauli matrices. Yeah. In other words, it's often easy to write down the basis, but they may not be orthogonal, right? So for example, in your homework, I think you will be asked to identify a basis for the polynomial. Right, so what's the basis of the space of that set of polynomials? Tell me. Let me start you off. That's the, sorry, that's the first basis vector. What's the other one? That's the constant. Give me another one. X, right? And then you have x squared, all the way to xn, right? So it's very easy to write down a basis. And so your question is, oh, well, it's so easy, so why don't we just stick with it, right? But in this case, you'll also discover that this basis is not orthogonal. This I'm sure, actually. I know because I know the Legendre polynomials. So if you try to work them out, you'll find that the inner product of, say, x to the 100 is not orthogonal to x to the 99, for example. There's some amount of overlap. Yeah. So you know that it's n-dimensional, but you need to find out what the orthogonal basis is. Okay, very good. So with the remaining time, I'd like to start a short discussion on, oh, I'm out of time. Then maybe I'll take another question. Any other questions? Yes.
Can I ask why
Yeah.
this trace or TR?
Trace?
Yes.
Do you know trace?
Yeah, I mean it's quite.
Why?
Yes.
What do you mean why?
Um,
Why are we using trace, you mean?
yes.
So this is one of your homework problems. You prove that the trace of the product two matrices, you will prove that this is a good inner product. So if you have A matrix and B matrix, right?
Yes.
So a way to define their inner product is to, in fact, take the trace of A dagger B. You will discover this. So you will have to, you know what that means, right? So you know we have A1 to A5 the other day, right? And so you have to make sure that you plug this definition into these axioms. In fact, in an earlier problem, the first step is, in fact, convince yourself that the set of matrices are a good vector space, right? So in fact, there was an earlier problem, if you remember. That's why I say, I always tell people, start the homework early. Because if you want to follow along, it will be very useful if you do the homework as we go along. So the first step is you show that the set of matrices are a vector space. And then, when it comes to square matrices, you can now introduce this trace, which, by the way, in index notation just means A dagger. So the ij component will be something like that, right? B, A, J. Okay, and when you take a trace, it just means you're summing over this guy. And you can show this notation may not be important for what we want to prove, but I wanted to show you exactly what the trace means. You're summing over the diagonal components, right? This definition, that's the key, is a good definition for the inner product, right? So for example, you have to show that the complex conjugate of this guy is just Bn. Right? I forgot which one was it, A2 or A3 or which, some one of them, right? This is one of the axioms, right? And you can show that this is true. So what I'm saying is that if you remember that, this is a good definition for the inner product, then this is saying that you can do a direct calculation and show that they are in fact orthogonal. Is that, yeah. Any other questions? All right. See you guys next week. Yeah.
What is this two? So
Oh, you have to calculate it.
Yeah,
So if you're wondering how to calculate it, I can give you a hint. So all this depends on the special properties of the Pauli matrices. Okay? So the Pauli matrices, if you're just looking at the spatial part, you take so I and J are 1, 2, 3. When you multiply sigma I, sigma j, you realize that you get Kronecker ij plus I epsilon ijk sigma k. Have you seen this before?
yesterday's contradiction.
Yeah, well, we haven't talked about this yet, but yes, eventually we'll talk about this. Yeah. But you should have seen it in a quantum mechanics course when you were in undergrad. Right. So this is what you should have. And then of course if you have sigma 0, remember sigma 0 is just the identity, right? So sigma 0 times sigma I is of course just sigma I. Okay. Now you do need to know that the trace of a single Pauli matrix is 0. And you do need to know that they are Hermitian. All of them are Hermitian actually. All of them are Hermitian. But they are important properties, so they're worth knowing. So I claim, based on all these facts, you don't need to actually multiply the matrices explicitly to do this trace. All these will allow you to do this, to conclude this fact. Okay? That's the clue for you. So if you want to try to do this chapter, I don't think it's in my homework, but I don't think it's a homework problem. But if you want, you can try this. Right? So these facts, use these facts and plug it into this trace, and I claim that you can calculate directly. You can verify directly the right-hand side. Right. So try it out. Put 0, 0, 0, I 0, and you will discover that is this result. Yeah.
Yeah, I can see.
You can see it. Very good.
Yeah,
Maybe you can
yeah,
explain.
okay.
Yeah, maybe you can explain the hint.